everybody, this is 10.2 for AP Stats Notes, and we are going to be looking at two sample problems for means. Our last one was proportions, now we're looking at means. The biggest idea here is that, again, if we're looking for a two sample, they should be coming from two independent populations, two different lakes if you're pulling out samples of fish, right? And if you're doing an experiment, you want to be able to say in there that these were two independent samples as well. So we're going to end up doing significance tests on difference of the two means. That means we have some conditions we need to look at. They're going to be all really similar to what you're used to before. When we have an SRS, we now have to make sure there are two SRSs explained from two different populations. We still have the large count, or really the normality rule here, which the nice thing is if they say the individual populations were normally distributed, then their differences should also be normally distributed as well. We do still have to check the large sample size if they don't give us that the original populations were normally distributed. And that will overrule, if you have a large enough sample size, non-normal distributions. So that means each individual population has to be more than 30. Okay, and then again, the 10% independence test, we are checking for samples are independent, that one sample has no influence over the other. Usually you can just say that in an experiment, right? That one sample has no influence over the other, they're completely independent. Also, samples are large enough to handle sampling without replacement. So you can still go back and check our usual way of 10 little n is less than or equal to big N. All right, so if we're looking at the difference of the two means, right, we want to be able to just be able to explain what that distribution should look like. So the distribution should look like, it should look normal. The differences of the two different populations should look normal. And if they don't say that they're normal, then if the sample sizes were large enough, we're still going to get a normal bell curve. The center, the mean difference, is just going to be our two sample means subtracted, and that should be what our population means are subtracted, right? If I sample enough times, take enough scoops, this is what we should be looking at, right? All right, and then the spread, the standard deviation. So this one is showing us it with sigma. Remember that often in a means test, you will not have sigma, you'll just have t. So we'll just replace that out whenever it happens. If we happen to know it, which is very rare, we will use sigma. If not, we're going to go ahead and use S sub x. And then this becomes, instead of standard deviation, remember that it now then becomes standard error instead. So standard error if this is not available. And we use S instead. Okay, so we're going to go through 3 examples just to make sure we're all good, and we'll show you some of the tricky stuff that happens with this, but I honestly think that the means problems in this section is easier to do two means than it is to do two proportions, so I think they switch a little bit. So in our first example, we have a potato chip manufacturer buys potatoes from 2 different suppliers. There's Riderwood Farms and Camberley. The weights of the potatoes are approximately normal, so we want to make sure we notice that. Okay, we've distributed with a mean of 175, a standard deviation of 25. That's their population numbers, right? That's not their sampling, that's their population numbers. The weights of potatoes from Camberley are approximately normal, with a mean of 180 and a standard deviation of 30. That's their population numbers, that's not their sampling numbers. When shipments arrive at the factory, inspectors randomly select a sample of 20 potatoes. So that's my sample size from each shipment and weigh them. So they're saying let the mean value from the Camberley farm subtracted from the mean weight from the Riderwood farm be the difference in the sample mean weight of the potatoes. So what is the shape of the sampling distribution? Well, the shape we want to be able to say is we want to be able to say that it is a normal shape, right? So how do we say that? Well, we say if both populations are normally distributed, then our difference of means should also be approximately normal distributed. okay? If it didn't pass that and they didn't give us normal, then we could go up and check the 30, right? But we don't even have to do that. All right, the next part, it says find the mean of the sampling distribution. All right, that's not so bad. That just means that we're going to go and find the mean of x1 bar minus x2 bar, and that should be the same as mu sub 1 minus mu sub 2. Okay, so what is that going to look like in our case as well? Let's take a look. We know our sampling difference should be the same as our parameter difference. I switch them out instead of 1 and 2 to C and R, so I know which ones they go with. So what this means is, because I set them up in an order, when I subtract, I get a positive, that the Kimberly Farms seems to have a little bit more in weight on the potatoes than the Riderwood Farms by about 5 grams. So the difference is approximately 5 grams. Let's do the finding the standard deviation. So let's go and write our formula first. All right, so because they gave us sigma, right, we're going to use that. We're going to keep the same subtraction. And remember, our normal formula for standard deviation for a means of something is usually just the sigma over the square root of the count, right? But we're going to have to add them together, which means I'm going to have to square them first, then add them together, then take their square root. So that's why there's a square root now around the whole thing. Plugged in our numbers, remember that they did a sample of 20 from each shipment, and we get 8.73 grams. So now we could draw our normal curve and say that the difference has a 5 right in the middle of that, and that it's an 8.73 spread. So basically this would be what our normal curve would look like. A couple points here. These would end up being, let's see, x sub C minus x sub R, right? When we're saying that the average amount is usually 5 grams, and then it's off by as much as 8 grams in either direction. So the difference could go up as high as 13, down just 1 standard deviation up to 13, 1 standard deviation down to negative. Those negatives aren't going to freak us out because it's just a difference. It's not the actual weight of the potatoes. So it's just the difference of the potatoes. It just means that the other side ended up having more of a weight to them than the other. So not a big deal to have pluses and minuses when they're talking about weights of stuff in a sampling or a comparison of two things. Let's see how fast we can do a confidence interval for means with 2 samples. Okay, so if we want to do a t-interval, right, we start out with our first guess. Going back to highlighting here, so my first guess is going to be whatever I can sample, right? Subtract what I can reach, and then I'm going to have a t-star because it's a confidence interval, and then I'm likely going to have my standard error, right? I'm probably not going to know my sigma, so it looks like that. But remember, for t-stars, we're going to need degrees of freedom, right? And now we have 2 different sample populations, and they can be different sizes. So this becomes really challenging. Here is the official formula for how to actually calculate DF. And this is not on our formula sheet, which means they don't think we need to know this. That's good. So we're going to call this ugly, okay, and say don't do this one, okay, because there is an easier one. So option 2 is to use your calculator. Yes, that's the one we really want to use. And then if you're truly desperate and your calculator dies, you can use the fewer of whichever sample size is smaller, subtract from 1. You'll be conservative, but then you could use table B or whatever is the table that includes the degrees of freedom. Okay, so we really want to do option 2 where we just have our calculator do it for us. All right, so in our example here, we're going to be comparing the number of chocolate chips in a Chips Ahoy cookie bag versus a Great Value cookie bag. They're going to randomly select 1 cookie from each bag after they randomly bought 10 bags of each type. Okay, and then they carefully broke about each one of those and counted the number of chocolate chips in each. Here are their results. So we've got 2 tables going on, right? Chips Ahoy and Great Value. Those are definitely 2 different populations, right? 2 populations, the ones that are Chips Ahoy cookies, the ones that are Great Value. I'm going to take a second and put this into my calculator under list 1 and list 2, and then I'll come back. All right, so you can see on my calculator screen that I've entered them both in list 1 and list 2. I've labeled them here, and now we're going to construct and interpret a 99% confidence interval. So that means we're going to be following the format of panic, and we do not have a lot of room to do that. So under the P part for panic, we want to tell them what we are using. We are using the true mean difference. So let's just go and do the shorter version. Let's go and do mu sub C minus mu sub G is equal to the true difference or true mean difference of chocolate chips in each brand of cookies. And then we're going to tell them which order that was. That was Chips Ahoy minus Great Value. Okay, next part is we need to go and do our assumptions. So do we have the random part? Let's go check our assumptions. So we're good with random because we randomly selected a cookie from each of the 10 bags, from each type of bag. We're good with 10% or the independence rule because we have 10 bags and 10 times 10 is still less than all the bags of cookies of each type out there. Normal, though, we're going to have a problem. They never said they were originally normally distributed, so I can't assume their subtraction is normally distributed. So I've got to check each one for more than 30. I don't have more than 30, so we're stuck looking at these graphs again, looking for heavy skews or outliers. So let me go and draw a graph up here and we'll talk about it really quickly. All right, so I put them into the graph and I turned on both list 1 and list 2. You can see plot 1 is on, you can see plot 3 is on, and each one is using its own list. But when I go to graph it, it's really, really challenging to try to compare these two. So the other thing that I could do is I could change the plot. Let's go and change them to maybe a box, a box and whisker plot for each one. So that was plot 1 and 3. I didn't use 2 because it's still got my word residual and I don't want to lose that. So let's go with, oops, got to go back up there. Hang on, turn this one on. We're going to go over to this one instead. And we're going to make sure this is list 2. That looks great. And then we'll do zoom 9 for this one. See, this one's a better picture for me for this one, right? Because now I can actually see what the two are. If I press trace, it tells me this is my Chips Ahoy, and this one is my Great Value, right? So I could go and copy this onto my graph. I would have to number it. I'd have to do all that stuff. We're going to skip that just to save a little bit of time. We know the other one has a mean that is or medium that's a little bit higher. Goes over that way. It goes almost right up to the same box that way. Goes way out here. Goes way out here. Okay. Does not look like we have any strong skew. So again, this is not the best graph. It's just a really quick one. No strong skew or outliers. Okay, so we will continue. All right, so then what's next? We need the name for this stuff. So the name is going to be a 2 sample, difference of means, T interval, right? We're running an interval. And then the next thing I want to do is start calculating the interval. So we start out with my guess. Now this is when I brought up my calculator, and I'm going to go over to stat tests. And remember, this is an interval, so we're going to be looking at the bottom half here from 7 to B. And these are not proportions. So I am looking for the one that says 2 sample Z or T, and the determination between those two depends on whether I, number 1, called it a Z or a T, and 2, whether I have the official standard deviation. We do not usually in means, so we're going to go ahead and do 0 here, the 2 sample T integer. This time I'm going to tell it, you go find the data. I'm not going to type it all in for you. So I'm going to do list 1, list 2, frequency, confidence level is 0.99. Remember, these are decimals. Pool, we only pool proportions. We only pool proportions. So on this one, you're going to always just say no. And then we're going to press calculate. Now it's going to give me what my actual interval is going to be at the very end. Remember, we want to show them how it works within the process. So we're going to start out with 18.4 minus 19.4. Then we're going to do plus or minus. We're going to do a T star. And then we're going to have to do the 2 standard deviations. So the first standard deviation is 1.776 squared over 10. And then the other one is 3.596 squared over 10. And we have to go and figure out what the T star value is. So if we have 99% here, then we only have 1% to split. So this is 0.005. So we're doing inverse T of 0.995, and I need degrees of freedom, and you'll see that it is on here, right underneath the standard deviations. Where did it go? There it is, 13.145. Cool, so we're gonna take that one. Now, if we didn't have our calculator and it died suddenly, we'd be using degree of freedom of 9. Find the smallest sample size, 10, subtract 1, it'll be conservative. Okay, so knowing that, we're gonna go and get our T star score. Is it on here anywhere? I don't believe it is. Right, so we're gonna have to go and calculate that on our own. So second vars, inverse T, we're gonna do 0.995. We're gonna say our degree of freedom is 13.145. And we're gonna paste that in just to get our T value into the formula. So this is going to be a 3.007. 3.007. Okay, and then I can turn this into my actual interval. So back to where we were before. Go over towards intervals. This was not a proportion, but it was a 2 sample. Okay, go all the way down, do not pool, calculate, and there is our interval. I should have written that down before. So negative 4.814 all the way to 2.813 or 2.814. Okay, so those are our two. And again, you want to make sure somewhere in here you have said what degrees of freedom are, right? So did I put that in anywhere? I did right here, but I didn't label it. So degrees of freedom equal. Cool. And then we just have our conclusion is the only thing left. So our conclusion is we are 99% confident that the interval from negative 4.814 to positive 2.814 captures the true difference. And then we go back up to here and write this back in, the true mean difference of chocolate chips in each brand, blah, 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 whatever they said in the beginning, okay? Last question says, does your interval provide convincing evidence that there's a difference in the mean number of chocolate chips? Now, if they didn't say, does your interval provide, we would have had to have gone and write up a whole phantoms, which we'll do next. But since they didn't, I'm just looking to see, is there a difference? So is there a difference means is zero in the interval? The 0 in the interval means it's very possible that there is no difference. So we would write that since the 0 is within this interval, we go from a negative to a positive, there is not convincing evidence. Okay, so we would say since our interval captures 0, there is not convincing evidence. Okay, and that's it. Next video, we'll go through a significance test with difference of means, and then we are done with chapter 10.